In this video lesson in nuclear chemistry, we are going to learn about natural radioactivity. To do that, we have to discuss the nuclear force. The nuclear force is the fundamental, extremely strong force that binds all of the nucleons in the nucleus together. The nucleons, of course, are the protons and the neutrons. It binds the protons to protons, the neutrons to neutrons, and the protons to neutrons in a very tiny space. Nuclear force is so strong it prevents tightly packed protons from repelling each other, because they're positively charged, due to their similar positive charges. A lot of times you're going to hear about whether a nucleus is stable or unstable. So that's what we're going to dive into next. Nuclear stability is based on the ratio of neutrons, which we're going to symbolize as N0, to protons, which we're going to symbolize as P+. So it's this ratio of neutrons to protons in the nucleus that determines whether or not the atom is stable or unstable. The ratio of neutrons to protons in a stable atom varies with its size. Small atoms are stable at a 1-to-1 neutron to proton ratio. Larger atoms are stable at a ratio as high as 1.5 neutrons to 1 proton. Any neutron to proton ratio outside these parameters results in an unstable nucleus, resulting in that atom being radioactive. Radioactivity is the act of emitting radiation spontaneously which means it can happen in a number of different ways, but all are considered to be nuclear reactions. And they differ from chemical reactions in that the original atoms are actually changed into atoms of another element, a concept known as transmutation. So nuclear reactions are reactions of the nucleus, very different from chemical reactions, which are due to interactions of electrons only. Now in this lesson, we're going to focus on naturally occurring nuclear reactions. We will look at artificial nuclear reactions in a later section of this unit. Okay. Our first natural decay, our natural radioactivity example, is what is called alpha decay. And this decay happens when there are just too many nucleons. Okay, so just too many protons and neutrons. The nucleus is just way too heavy. So the key here is that the white particles are neutrons, and the gray particles are protons, right? And so this is the, right here, this is a large, unstable nucleus. And it is emitting, this right here means it's emitting, it emits an alpha particle, which is 2 protons and 2 neutrons, right? That's what this is called, is an alpha particle. So this alpha particle came, you can see in this diagram, it's kind of circled right here. Okay? It's just plucking 2 protons and 2 neutrons out of the nucleus of this large unstable nucleus, right? And so we sometimes will refer to this, you'll see it symbolized as 4/2 He, but it's referred to as an alpha particle. And the result is a smaller, less unstable, meaning more stable, which is an awkward way of saying it, but it's a smaller nucleus of a different element. So the idea here is that, yes, this is more stable than this nucleus, but this nucleus is probably also still radioactive. So that's why I said it's less unstable. It is more stable, but it's probably still radioactive. It's probably still going to have some changes. But this act of emitting an alpha particle is symbolized here. So here is a nuclear change represented in equation form. Uranium is 238 over 92, the mass number of 238. The atomic number of 92, right? This arrow means the change is happening. An alpha particle is produced, so we're going to write that on the product side of this arrow, right? So we started with this. This breaks apart into two things, right? The alpha particle is one of those things. Now, what is this other thing? What element is it? Well, this is where you have to do some simple arithmetic, as long as you consider that this arrow is an equal sign. 92 is equal to 2 plus something, so that has to be 90. The mass of 238, now it's 4 nucleons lighter, so the resulting mass is 234. We can identify this element. The element, the atomic number 90 corresponds to thorium, Th, right? And so this equation here represents alpha decay, because we see an alpha particle on this heavy alpha particle. Right? And then we see this lighter nucleus. Okay. Now let's go ahead and take a look at natural decay example number 2. Okay. This one is going to be known as beta decay, and this one is going to happen when there are just too many neutrons. So what we have here is the neutrons are these white particles, the gray are the protons, and it's hard to tell in this diagram, but there are just too many neutrons. So a description of what's about to happen is that a neutron disintegrates. Basically, it turns into two things. Turns into a proton. And now it can't just do that like without something else coming out of it. So a neutron turns into a proton, which is positively charged, of course, and an electron, which is negatively charged. So you can see you have one of each. That's going to be neutral, right, with the mass of a proton. So effectively you have a neutron is going to turn into a proton. But now this electron is not an electron that was orbiting around the nucleus. This electron is actually being, the source is the original neutron. Okay. And so this right here, this electron is what we call the beta particle. And we usually let it symbolize as it has a mass of 0, a charge of -1, and we'll symbolize it with an E for electron. So let's see what that looks like in an equation form. Right? In an equation form, if we have carbon 14, carbon has an atomic number of 6. Right, so we're starting out with carbon 14. We see that it's going to give off a beta particle, so we're going to symbolize that as 0 over -1e. Now, what is this atom once this beta particle is emitted by this neutron? Well, let's go back to that math, right? 14 is equal to 0 plus 14. So the mass is going to going to stay the same. But in this case, 6 is equal to -1 plus 7, or 7 minus 1 is equal to 6. Okay, so atomic number 7, we're looking at nitrogen. So we've turned carbon into nitrogen. The mass has stayed the same, right? Let's make note of that. The mass is the same. But notice that the atomic number increases by 1. Right? So the effect here, this originally had 8 neutrons. 14 minus 6 is 8 neutrons. 14 minus 7 is 7 neutrons, right? So this atom has reduced the number of neutrons, and that neutron has turned into a proton. We see the protons increasing. Okay. So here we see a neutron turns into a proton plus a beta particle. All right, the third type of natural decay is known as positron decay. And this is going to happen when there are too few neutrons. So what we see here is a nucleus here, too few neutrons. So now what we're going to have happen is we are going to see a proton, kind of the opposite of what we just saw with beta decay. A proton is going to disintegrate, or basically turn into, two things. It is going to turn into a neutron, and then something called a positron. Okay? A positron is a small particle. Think of it as a positive electron. So it's a tiny particle with the mass of an electron, but it has a positive, not a negative charge. So let's see what that might look like in equation form. Here we have potassium 38. Potassium has an atomic number of 19. Oh, let's go back up and right this here. Let's label this. This is the positron, right? You can see it has the positive charge, but it's not a proton. It's the mass of an electron. So we're going to symbolize it as a mass of 0, a charge of +1, and an E, or basically a positive electron. All right, so let's see. This potassium 38 is going to emit this positron particle, this positively charged electron that came from the nucleus. A proton spits out this positron and turns into a neutron. But when this positron is emitted from this potassium 38, what is the particle that's left over? Let's do the math. 38 is equal to 0 plus 38. 19 is equal to 1 plus 18. So this now is the element argon. If we take a look here in terms of the number of neutrons, 38 minus 19 is 19 neutrons. And we end up with 38 minus 18, we end up with 20 neutrons, right? So we've increased the number of neutrons by decreasing the number of protons. Let's take a look here. What do we see here? We see that the mass has stayed the same, but we see that the atomic number decreases by 1. All right, let's take a look at natural decay example number 4. This is what is called gamma radiation. This happens when an atom just has too much contained energy. Right, so this is, the nucleus is in some sort of excited nuclear state. It emits radiation in the form of gamma rays. This is the Greek symbol for gamma. The idea here is that the nucleus releases energy. Whoa, spelling. The nucleus releases energy, but there is no change in the number of protons or the number of neutrons. How do we represent this in equation form? This is technetium with a total mass of 93. You'll notice the M means meta, which means it is just sort of the high energy state. What we have here is we're going to represent the gamma radiation, which has a mass of 0 and a charge of 0. And it's just going to turn into technetium-93. Okay, so there's no change in this substance, whatever, other than its energy state. The fifth natural decay example is something called electron capture. And this is interesting because in this case, the nucleus is actually going to capture a first shell electron and incorporate it into its nucleus. This can happen when the atom or the nucleus just has too few neutrons. Right, so this was accomplished when an atom had too few neutrons. It could do positron decay, right, or it can do electron capture. So this is now an electron. Spelling. This is an electron from the first principal energy level, the first shell. Okay, so it's actually going to grab an electron that's orbiting outside the nucleus, and it's going to bring it into the nuclear structure. This is energy producing, right? So this is a way for an atom to shed some of its high energy too. That's another, what do I want to say? Another artifact of what happens here. But the description of this nuclear change is that a proton absorbs / fuses with an electron from the first shell, and the net effect is that the proton turns into a neutron. How do we represent this as an equation form? We've got samarium 145. Samarium is atomic number 69. This time we're going to show that electron, that zero mass, -1 charge, E. We're showing it now on the left side because this atom is going to fuse with this electron. Let's do the math, right? So 145 plus 0, we're going to end up with a mass of 145. 69 minus 1, we're going to end up with an atomic number of 68. This is going to turn into erbium. We can also represent those X-rays. X-rays have a mass of 0 and an atomic number of 0. And we'll call it X for X-ray. But what we can see here is 145 minus 69, that's going to give us 76 neutrons. 145 minus 68 is going to give us 77 neutrons. So you can see here that the number of neutrons increases while the number of protons decreases. Okay, so that's effectively a proton turning into a neutron there. All right, well, let's talk about these particles that we've been talking about, the positron, the beta particle, the alpha particles. These are collectively called emanations, right? Emanations are the particles or the emissions released when a nucleus disintegrates. There's a reference table for this that kind of organizes the name of those particles, the notation that we use when we're trying to write these nuclear reactions in an equation format, the symbol that's sometimes used to represent them. We're going to add into this the mass and the charge, right? So just remember, the top number is what we call, when we see a symbol like this, the top number is the mass, okay, and the charge of the nucleus is going to be the bottom number. Okay, so it's the atomic number, but effectively it becomes the charge of the particle because we're talking about the nucleus, and the nucleus only has positively charged particles. So the alpha particle with a mass of 4 and a charge of 2. We can see that this is the Greek letter alpha, sometimes used to symbolize this. A beta particle, which is really just an electron, has a mass of 0 and a charge of -1. This is a Greek letter beta, so sometimes you'll see a beta particle written with a -1 charge. That is the same. So you just need to recognize that those all mean the same thing. Gamma radiation, mass of 0, charge of 0. A neutron has a mass of 1 and a charge of 0. A proton, which is the same thing as a hydrogen nucleus, has a mass of 1 and a charge of +1. And a positron, which we said is a mass of 0, but a charge of +1, sometimes written as a beta plus symbol. So Table O has this information and all the symbols that are available to you, so you do not have to memorize those symbols and that notation. Penetrating power is the ability of radiation to pass through matter. Gamma rays have the most penetration power, and alpha particles have the least penetrating power. So alpha particles get stopped by paper. They can't go through paper. Beta particles can go through paper, but they're stopped by aluminum. And gamma rays are not stopped by paper or aluminum, or even lead. Gamma rays can even go through lead, although some of it gets trapped. They're trying to indicate that some of it gets trapped there. All right, identifying radioactive elements on the reference tables. You can tell which elements are radioactive because the atomic mass is in parentheses. On the classroom periodic table, you'll see that they are in white. The letters are often written in white. Elements with an atomic number of 83 and higher. Every isotope, we're going to add into this, every isotope of all those elements, 83 and above, are all radioactive. They're all unstable. Elements up to and including 82, right, have at least one stable isotope. So it doesn't mean that all the isotopes 82 and lower are all stable, and there's no radioactivity there, because that's false. But at least one isotope is stable with an atomic number of 82 or lower. Atomic number 83 and higher, every isotope of all those elements are all unstable. All right, so in this video lesson, we learned about natural radioactivity, how we symbolize it in a chemical equation format. We call them nuclear reactions because they are reactions that are all happening inside the nucleus. And we talked about the stability of atoms is due to the neutron to proton ratio. And that's how it ties back in with the nuclear force, which is a very strong force between the nucleons. That's it for this video lesson. We'll see you back in the classroom.